Chaos theory is a fascinating branch of mathematics and science that examines how small changes in initial conditions can lead to vastly different outcomes, a phenomenon often illustrated by the butterfly effect. This concept suggests that a minor event, such as the flapping of a butterfly's wings, could ultimately influence significant occurrences, like the formation of a tornado weeks later. Chaos theory is not just an abstract mathematical idea. It has profound implications in various scientific fields, including meteorology, engineering, economics, and biology. In everyday life, we often encounter situations where seemingly trivial decisions or actions can lead to unexpected and sometimes dramatic results, underscoring the relevance of chaos theory in our understanding of complex systems. The relationship between small events and large outcomes challenges the traditional deterministic views that have dominated scientific thought for centuries. In a deterministic framework, the future is entirely predictable if we have complete knowledge of the present state of a system. However, chaos theory reveals that even with precise initial conditions, the long-term behavior of certain systems can be inherently unpredictable due to their sensitivity to initial conditions. This unpredictability does not imply randomness, but rather a complex interplay of factors that can lead to emergent behaviors. As we delve deeper into chaos theory, we begin to appreciate the intricate patterns and structures that can arise from seemingly chaotic systems. This exploration invites us to reconsider our understanding of order and disorder in the universe, prompting questions about control, predictability, and the nature of reality itself. By embracing the principles of chaos theory, we can gain a richer perspective on the complexities of the world around us, ultimately reshaping our approach to both scientific inquiry and everyday decision-making. The universe operates through two fundamental modes, probabilistic and deterministic, each offering a distinct perspective on how events unfold. The probabilistic mode is characterized by chance and unpredictability, where outcomes are not fixed, but rather influenced by a range of possible variables. In this framework, events are often described in terms of probabilities, reflecting the inherent uncertainty of certain systems. For instance, quantum mechanics exemplifies this mode, where particles exist in a state of superposition until measured, leading to various potential outcomes. This probabilistic nature highlights the role of randomness and chance in shaping reality, suggesting that not everything can be predicted or controlled. In contrast, the deterministic mode is rooted in predictability and cause-effect relationships. In this view, if we have complete knowledge of a system's initial conditions, we can accurately predict its future states. Classical mechanics is a prime example of this mode, where the motion of objects can be precisely calculated based on their initial positions and velocities. Determinism implies a structured universe governed by laws that dictate how events unfold, reinforcing the idea that every effect has a specific cause. Interestingly, these two modes coexist and interact in shaping our reality. While many systems exhibit deterministic behavior, such as the orbits of planets, they can also display probabilistic characteristics, especially at microscopic levels. For example, while we can predict the trajectory of a thrown ball with great accuracy, the exact position of a subatomic particle remains uncertain until observed. This interplay between deterministic and probabilistic modes enriches our understanding of the universe, illustrating that while some aspects of reality may be predictable, others remain shrouded in uncertainty. By acknowledging both modes, we can better navigate the complexities of existence, appreciating the balance between order and chaos that defines our world. Chaos theory is a captivating field of study that explores how small events can lead to significant and often unpredictable consequences. One of the most famous illustrations of this concept is the butterfly effect, which posits that the flapping of a butterfly's wings in one part of the world could ultimately set off a chain of events leading to a tornado in another region. This metaphor encapsulates the idea that minor changes in initial conditions can dramatically alter the trajectory of complex systems, emphasizing the interconnectedness of events in our universe. The implications of chaos theory extend far beyond mere metaphors. They provide valuable insights into understanding complex systems across various disciplines, including meteorology, biology, economics, and even social sciences. In these fields, systems are often influenced by numerous variables that interact in intricate ways, making them sensitive to initial conditions. For instance, in weather forecasting, a small error in measuring temperature or humidity can lead to vastly different predictions, illustrating how chaotic behavior can emerge from seemingly simple systems. Central to chaos theory is the importance of initial conditions in determining outcomes. In a chaotic system, even the slightest variation can lead to divergent results over time, making long-term predictions exceedingly difficult. This sensitivity highlights the limitations of traditional deterministic models, which assume that systems behave predictably when initial conditions are known. Instead, chaos theory reveals that unpredictability is an inherent characteristic of many natural phenomena, challenging our understanding of order and control. By embracing chaos theory and the butterfly effect, we gain a deeper appreciation for the complexity of the world around us. It encourages us to recognize that our actions, no matter how small, can have far-reaching consequences, prompting a more thoughtful approach to decision-making in both personal and societal contexts. Ultimately, chaos theory invites us to explore the delicate balance between order and chaos that shapes our reality. Chaos theory can be vividly demonstrated through an engaging exercise known as the chaos game, which illustrates how simple rules can lead to complex and structured patterns. To begin, imagine an equilateral triangle drawn on a piece of paper. The first step in the chaos game is to identify and label the three vertices of the triangle as points A, B, and C. Next, you will randomly place a dot anywhere inside the triangle. This dot serves as your starting point. The next steps involve a simple yet powerful rule. Repeatedly choose one of the three vertices at random and move the dot halfway toward that vertex. For instance, if you randomly select vertex A, you would take the current position of your dot and move it to a point that is halfway between its current location and point A. After this move, you continue the process by randomly selecting a vertex and repeating the halfway movement. By doing this multiple times, you will notice that what initially appears to be a random scattering of dots begins to form a recognizable pattern. As you continue this process, the seemingly random dots will converge to create a strikingly structured pattern known as the Sierpinski triangle. This fractal pattern showcases how chaos theory operates, revealing that order can emerge from randomness through simple iterative processes. The Sierpinski triangle is not only visually captivating, but also serves as a profound example of how complex structures can arise from basic rules. For those interested in hands-on learning, I encourage you to try the chaos game yourself. You can use graph paper or a digital drawing tool to replicate the steps outlined above. By experimenting with different starting points and observing the resulting patterns, you will gain a deeper understanding of chaos theory and its implications. This interactive approach not only reinforces the concepts of chaos theory, but also highlights the beauty of mathematics in revealing the hidden order within chaos. Deterministic systems, which are governed by specific laws and rules, can surprisingly become unpredictable over time due to their inherent sensitivity to initial conditions. To illustrate this concept, consider a simple mathematical process, multiplying a number by a constant and then removing some of its digits. For example, if we start with the number 0.1 and multiply it by 3, we get 0.3. If we then remove the digit after the decimal point, we are left with 3. Continuing this process, we can see how small changes in our initial number, or the digits we choose to remove, can lead to vastly different outcomes. This exercise highlights how even a deterministic process can yield unpredictable results. If we were to start with a slightly different initial number, say 0.11 instead of 0.1, the subsequent multiplications and digit removals would lead to a completely different sequence of outcomes. This illustrates the concept that small errors or variations in initial conditions can lead to significant deviations over time, a hallmark of chaotic behavior. In chaotic systems, this critical dependence on initial conditions is what makes long-term predictions nearly impossible. Even the tiniest discrepancy in the starting point can result in a dramatically different trajectory, as seen in weather patterns or the behavior of certain ecosystems. For instance, a minor change in temperature or humidity can lead to vastly different weather outcomes days or weeks later. Understanding how deterministic systems can evolve into unpredictable ones emphasizes the complexity of the natural world. It challenges our assumptions about predictability and control, reminding us that while we may operate within deterministic frameworks, the outcomes can still be profoundly influenced by small variations. This interplay between order and chaos invites us to appreciate the intricate dynamics that govern our universe, revealing the delicate balance between predictability and unpredictability in our lives. Fractals are intricate geometric shapes that exhibit self-similarity across different scales, meaning that their structure remains consistent regardless of how closely you examine them. This property allows fractals to reveal complex patterns that repeat infinitely, creating a sense of order within apparent chaos. Fractals can be found in various forms, from simple mathematical constructs to complex natural phenomena, and they play a significant role in chaos theory by illustrating how complex structures can emerge from simple iterative processes. The work of mathematician Benoit Mandelbrot was pivotal in advancing our understanding of fractal geometry. In the late 20th century, Mandelbrot introduced the concept of fractals to a broader audience, demonstrating how they could be used to describe irregular shapes and patterns found in nature. His groundbreaking book, The Fractal Geometry of Nature, highlighted the importance of fractals in various fields including physics, biology, and economics. Mandelbrot's exploration of fractals provided a new lens through which to view complex systems, emphasizing that many natural forms, such as coastlines, clouds, and mountain ranges, cannot be accurately represented by traditional Euclidean geometry. Fractals are prevalent in nature, serving as a bridge between chaos theory and the natural world. For instance, the branching patterns of trees, the structure of snowflakes, and the formation of coastlines all exhibit fractal characteristics. These natural fractals often arise from chaotic systems, where small changes in initial conditions can lead to vastly different outcomes. The self-similar patterns found in these natural phenomena reflect the underlying principles of chaos theory, illustrating how order can emerge from seemingly random processes. By studying fractals, we gain valuable insights into the complexity of the universe and the interconnectedness of various systems. They serve as a reminder that chaos and order are not mutually exclusive, but rather intertwined aspects of the natural world. Understanding fractals enhances our appreciation of the beauty and complexity inherent in both mathematics and nature, revealing the profound relationships that exist within chaotic systems. Feedback loops play a crucial role in creating chaotic behavior within various systems, including ecosystems and markets. A feedback loop occurs when the output of a system influences its own input, leading to a cycle of interactions that can amplify or dampen changes. In ecosystems, for example, predator-prey relationships exemplify feedback loops. When a predator population increases, it can lead to a decline in the prey population. As the prey becomes scarcer, the predator population may eventually decrease due to a lack of food, allowing the prey population to recover. This cyclical interaction can lead to fluctuations in both populations, demonstrating how feedback loops contribute to the dynamic balance of ecosystems. In economic markets, feedback loops also play a significant role in influencing fluctuations. For instance, when stock prices rise, investor confidence typically increases, prompting more people to buy stocks. This increased demand can drive prices even higher, creating a positive feedback loop. Conversely, if stock prices begin to fall, panic selling can ensue, leading to further declines in prices as investors rush to exit the market. These feedback mechanisms can create volatile market conditions, where small changes can lead to significant and unpredictable outcomes. The interconnectedness of systems is a key factor in the emergence of chaos. In both ecological and economic contexts, feedback loops illustrate how individual components interact and influence one another. This interconnectedness means that a change in one part of the system can have far-reaching effects, often leading to unexpected and chaotic behavior. For example, a drought in one region can impact food supply chains globally, affecting markets and ecosystems far removed from the initial event. By understanding the role of feedback loops in creating chaotic behavior, we gain insights into the complexities of both natural and human-made systems. Recognizing these dynamics helps us appreciate the delicate balance that sustains ecosystems and economies, highlighting the importance of considering interconnectedness when addressing challenges in these systems. The uncertainty principle, a fundamental concept in quantum mechanics, asserts that certain pairs of properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision. This principle, formulated by Werner Heisenberg, reveals that the act of measuring one property of a particle inherently affects our knowledge of another property. For instance, if we precisely measure the position of an electron, we introduce uncertainty into its momentum, and vice versa. This intrinsic limitation challenges our classical intuitions about measurement and predictability, fundamentally altering our understanding of the behavior of particles at the quantum level. In contrast to quantum mechanics, Newtonian physics operates under the assumption that, given complete knowledge of a system's initial conditions, one can predict future states with certainty. Classical mechanics relies on deterministic laws, where the motion of objects can be calculated precisely based on their initial positions and velocities. However, the uncertainty principle highlights a stark departure from this deterministic view, illustrating that at the quantum level, unpredictability is an inherent characteristic of nature. This shift from certainty to uncertainty underscores the limitations of predictability in quantum systems, where randomness plays a crucial role. Moreover, the limitations of predictability extend beyond quantum mechanics into classical systems as well. While classical physics may appear deterministic, real-world complexities, such as chaotic behavior in dynamic systems, can render long-term predictions unreliable. For example, weather systems, governed by classical physics, exhibit chaotic characteristics where small variations in initial conditions can lead to vastly different outcomes. This unpredictability mirrors the uncertainty principle's implications in quantum mechanics, emphasizing that both realms possess inherent limitations in predictability. Ultimately, the uncertainty principle serves as a reminder of the complexities of the universe, challenging our assumptions about measurement and predictability. It highlights the delicate interplay between knowledge and uncertainty, urging us to reconsider how we approach understanding both quantum and classical systems. By acknowledging these limitations, we can better navigate the intricacies of the natural world and appreciate the profound implications of uncertainty in our quest for knowledge. The development of chaos theory has its roots in the pioneering work of Edward Lorenz, a meteorologist whose research in the 1960s fundamentally transformed our understanding of complex systems. Lorenz's journey into chaos theory began with his attempts to create a mathematical model for weather prediction. While running simulations on a simple weather model, he discovered that small changes in initial conditions could lead to vastly different outcomes. This realization emerged when he rounded off a number in his calculations, leading to a completely different weather forecast. This phenomenon, which he later termed the butterfly effect, illustrated how sensitive systems could be to initial conditions, emphasizing that even minor variations could result in significant and unpredictable changes. The significance of the butterfly effect extends beyond meteorology. It serves as a crucial concept in understanding complex systems across various disciplines. The idea that a butterfly flapping its wings in one part of the world could ultimately influence a tornado in another region encapsulates the interconnectedness of events in chaotic systems. This insight has profound implications for fields such as ecology, economics, and engineering, where small perturbations can lead to large-scale consequences. Chaos theory emerged as a response to traditional deterministic views that dominated scientific thought for centuries. Classical physics operated under the assumption that if one had complete knowledge of a system's initial conditions, future states could be predicted with certainty. However, Lorenz's findings challenged this notion, revealing that many systems, particularly those that are nonlinear and dynamic, exhibit unpredictable behavior despite being governed by deterministic laws. This shift in perspective opened the door to a new understanding of complexity, where order and chaos coexist, and where predictability is limited by the sensitivity of systems to initial conditions. In summary, the historical development of chaos theory, spearheaded by Edward Lorenz, has reshaped our understanding of complex systems and their inherent unpredictability. The butterfly effect serves as a powerful metaphor for this complexity, highlighting the limitations of traditional deterministic views and paving the way for a deeper exploration of chaos in various scientific fields. In this discussion, we have explored the fascinating realm of chaos theory, highlighting its key concepts such as unpredictability and interconnectedness. At its core, chaos theory reveals that even deterministic systems can exhibit unpredictable behavior due to their sensitivity to initial conditions. This unpredictability is beautifully illustrated by the butterfly effect, where small changes can lead to significant and often unforeseen consequences. We also examined how feedback loops in ecosystems and markets contribute to chaotic behavior, emphasizing the intricate relationships that exist within complex systems. Understanding chaos theory is not just an academic exercise, it has profound implications for both science and our daily lives. By recognizing the unpredictable nature of various systems, we can better navigate challenges in fields ranging from meteorology to economics, and even in our personal decision-making. Embracing the principles of chaos theory encourages us to appreciate the complexity of the world around us, fostering a mindset that is adaptable and resilient in the face of uncertainty. As we conclude this exploration of chaos theory, we invite you to engage with us further. If you found this content insightful, please consider subscribing to our channel for more thought-provoking discussions on complex topics. Your support helps us continue to create valuable content that deepens our understanding of the world. Don't forget to like this video and share it with friends and family who might also be interested in the intriguing dynamics of chaos theory. Together, we can foster a community that appreciates the beauty of complexity and the lessons it offers in both science and everyday life. Thank you for joining us on this journey, and we look forward to exploring more captivating subjects with you in the future.